Hello, everyone. I'm Zijian Zhang from ByteDance System Technologies and Engineering team. And today I will talk about a lightweight zero copy notification mechanism. So let's get started. Here is the agenda. Firstly, we will talk about the background of send message zero copy, along with its potential problem. And then I will go through the design and the implementation of our solution. And finally, I will talk about the evaluation and next steps. So Linux supports various interfaces that avoid copy, such as sendfile and splice. And in Linux 4.14, William added a message zero copy flag, which extends the copy avoidance mechanism to common socket send message system calls. The users can directly pass the flag to send message, and the underlying transmission will be zero copy. As implemented, copy avoidance is not a free lunch. It actually replaces the overhead of copy with page management and completion notifications. The send message zero copy needs hardware to support standard scatter-gather and transmission checksum offloading. Unlike zero copy in the receive path, there's no requirements on how memory blocks need to be sized and aligned. Most of the modern NICs support these features. Here is a typical code block of send message zero copy. So the users can firstly set up the socket option with zero copy, and then transmit the packets with send message calls with the message zero copy flag. And then after that, the users can use poll and receive message system calls to get the notifications. After the notifications, the buffer which is passed into the send message call can be safely reused and released by the user. In the read notification function, the users can parse the information in the control message. The users can check if the control message type is IP receive arrow or not. If so, the users can get the notification range from arrow info and arrow data. As you may notice from this code block, besides the overhead of send message zero copy system call itself, it actually introduces two extra system calls for the notification reception. Assume that applications which make use of send message zero copy are very sensitive to CPU usage. Extra system call overhead might be unignorable for this kind of applications, especially after the introduction of page table isolation to mitigate vulnerabilities like meltdown. The overhead of system call is much more. So how to return some information back to the user upon returning of send message without introducing extra system calls? It turns out that we already have similar mechanism in receive message. So in receive message, the users can pass message control as a placeholder. And upon returning of the receive message, the kernel will update the data in the message control so that the users can directly make use of it. So in this example of timestamping, the users pass a buffer with 512 bytes as a placeholder. And after returning of the receive message, the users can directly print out the timestamp. So the data layout in the message control will be like this, just like an array of entity. And each entity is composed of a header and data, so that the users can simply make a for loop to iterate through all of the entities, and then retrieve the information they want. In this case, the users will print some information about the timestamp. So how about message control in send message? It turns out that message control in send message is mainly used to send some information from the user space to the kernel space. So in this transmit timestamp self-test example, the users send a control message with type timestamping to the kernel to tell the kernel, you need to return what kind of timestamp back to me. And after the returning of send message, the users can once again use receive error message to get some information from the kernel. So what if we can support like passing message control as a placeholder to send message, just like receive message? So here we are trying to support message control copy back to user in the send message. In this code paradigm, the users can pass a message control as a placeholder and set the control message type to zero copy notification type to the send message. And we assume that upon returning of the send message, the users can get the zero copy notification directly. And just like the function print packet in the receive message example, the users can use the function like print zero copy info, which iterates through the control message to get the corresponding zero copy notifications. So in this case, the users can check the control message type if it's equal to CC notification, and if so, the users can deal with the notification, either print out or release the buffer. And to avoid compromising the original message control usage in send message, we make our new feature completely compatible with the original usage of message control. So in this example, the users can not only pass control message as a placeholder, but it can also pass the timestamping control message as usual to guide the kernel to do something with the timestamping. And upon returning of the send message, the users can remain the logic of timestamping the same. We assume that after returning of send message, the data of the placeholder will be updated. A problem with this design is that we expect some information will be returned right after the returning of send message. However, in send message zero copy case, after the returning of the send message, at that time, the underlying transmission might be uncompleted. Thus, there's no notification returning back to the user. So how do we deal with the trailing notifications, which means the notifications for the last several send messages? We probably might miss them. So how do we deal with it? We solve this problem by make our new notification mechanism totally compatible with the original one. So for the last several send messages notifications, the users can always use the original method as a backup to get the trailing notifications. And the users can even interleavely use these two methods or use them in hybrid mode. And here is all about the design. And before we dive into the details of the implementation, let's firstly review the current message control logic in send message. So in structured message header, there's a union, which includes either message control, a kernel buffer pointer, or message control user, which is a user pointer. And guided by the bit flag message control is user, the kernel knows what kind of pointer is stored in this union, so that the kernel can read from and write to the pointer in the union properly. And in send message, the message control, which was a user pointer, is actually overwritten by send message, either by kernel stack pointer or a pointer allocated by sock kmalloc. And the send message will set the message control is user bit flag to false. I guess the reason why send message did this is to for the convenience of further access in the kernel to avoid like further copy from user. So here comes to our implementation. We are trying to support a generic message control copy back framework for send message path. So in this case, we introduce a new bit flag for the message header, which is message control copy to user. And before returning of the send message, we will firstly check this bit flag. And if so, we will try to copy some control message back to the user on demand. In this function, we firstly create a message header from the message sys and update the bit flag message control is user to true, and then update the message control pointer to the original pointer, which is passed in by the user. And then using a for loop, we can copy the control message back to user on demand. Put message function is used here to handle compatible cases to support both 32-bit and 64-bit program. So how to make use of this framework in our zero copy notification? We can firstly add our flag in this function, which is used in the for loop of this function. And then in the specific handler of this control message type, we can get the information from message arrow queue, which is the same as the original method. And we can directly populate the kernel buffer control message with the information. And then finally set the bit flag to true. So overall, in our method, in sysend message, we will firstly initialize message control copy to user to false, and let the specific control message handler to update the kernel buffer, and then set the bit flag to true. And before returning of sysend message, we will try to copy something back to the user. And then we will use message zero copy self-test to evaluate our method. We add our new feature in this self-test. So the setup of this self-test is that there are two localhost sockets, one for sending and another one for receiving. The sending sockets will keep calling send message in this busy while loop for some certain of time. And then after some number of send messages, it will try to receive all of the remaining completions. The output of the self-test is the throughput in this time interval. The higher the throughput, the better the performance is. So here's our result. When we set notification interval to 1, which means after each one of the send message, the sending socket will try to get all of the remaining completions. So in this case, in TCP, we have around 16% in performance gain, and in UDP, we have around 20%. When we set notification interval to 32, which means the sending socket will get all of the remaining completion notifications after 32 of send messages. So which means less poll and receive message overhead for the original method. So in this case, for TCP, we have around 7% performance gain. And for UDP, we only have slightly performance optimization. So the reason for the difference in TCP and UDP is that in the context of the local host test of the self-test, the notification of TCP is more likely to be out of order. So the notification for UDP is more likely to be coalesced, which means less overhead of receive message. And that's the reason for the performance difference. And another problem with our implementation is that even if the users do not use this feature, in the hot path of send message, a minor cost of initialization of this bit flag and the check condition is added. So for the other possible use cases of our mechanism, I can think of is timestamp. So for this example, in the self-test of transmission timestamp, the kernel needs to return some information of timestamp back to the user. So as you can see from this code block, it's very similar to send message zero copy. The users firstly set up the socket option with a bunch of timestamping, and then transmission with the send message call. And after the send message, the users will receive the timestamp information using the combination of poll and receive message from the arrow message queue. Another possible use case of this might be HOMA. So HOMA is a receiver-driven low latency protocol. It has different socket API with the common sockets. So in the send message API of HOMA, it actually needs to pass an argument down to the send message. And upon returning of the send message, the ID of the arguments needs to be updated so that the user know what's the ID of this send message. So HOMA kind of like hacking the kernel by setting the arguments to the pointer of the arguments to message control and set message control length to 0 to bypass the overwriting in the send message. So it kind of compromises the semantics of message control in send message. So maybe in the future, HOMA can make use of our method. And maybe there are other possible use cases. As long as the kernel needs to return something back to the user via send message, our methods can be useful. So in summary, today we introduced a lightweight zero copy notification mechanism to save the overhead of extra system costs. And we have a generic message control copyback framework in send message, potentially apply to any other use cases where we need to return some information back to the user space. Our latest patch set is in this link, and thanks for the code reviewing and suggestions by William and Xiaochun. Do you have any comments and questions?
One question, if we're returning data in send message, does that imply, like in the completion case, that it has to be a blocking system call?
It doesn't need to be. So in the case when there is no notification, the send message will just return with like an empty notification. It will not block.
Right, but then in that case, I don't get the completion, so I still have to do something else, right?
Yeah.
So it's not clear to me how that scales, right? Because a lot of people are doing send message non-blocking. I'm wondering, is there like a possible alternative to maybe create a new socket type that its sole purpose is to collect these completions, and then I do a single receive message, and I can process multiple completions from multiple sockets? Something like that possible?
The reason why we introduced this kind of mechanism is we try to mostly reuse the original mechanism. So by introducing a new type of socket, I think it's possible, but it might cannot reuse most of the original code.
To an extent, but you're also modifying core send message, which, yeah, it's a minor performance hit, but that's across like everyone calling send message today. So I'm not exactly sure that that trade-off is really worth it. Either maybe a new system call or something like that, or use some other trick. So it's interesting, but yeah, this blocking semantics of forcing blocking semantics of send message do concern me.
Okay, thank you.
Hi. So I think I'm the only person who reviewed it. First of all, great presentation, very clear. Thanks for doing that, because I think it is good to get more feedback on this, particularly the point of adding a tiny bit of cost to everything for workloads that are, there aren't that many that use this. So that's been my feedback as well so far. On your point, we have also in the past, this has come up multiple times, to have a separate socket for completions across sockets, also to be able to close a connection and still reap these completions later. So I think those are orthogonal. Like in this case, it's essentially stealing from a receive message error queue. So that's always the option still. Yeah, I think my main concern is that whether the performance benefits for users of this code outweigh the cost of adding it. I think through all the revisions, you've basically taken most of the feedback that I've had already, so I don't have a lot. Maybe a static branch is sufficient to, satisfy that. But otherwise, this is, if we're going to do sort of piggybacking of receive metadata on send message, I think the implementation.
Thank you.
Hello. So one comment, like, so from the tone, in this use case, mostly it's async. So anyway, that like notification is not synced. it need to be like, release late. So that's for all the use cases. So another thing is like this is thing is important, right? So it's like from the RPC side, it's mostly used this way, right? Send, receive. So it's piggyback. Actually, is very efficient in that way, right? If we want to, use to extra that system call, right? So that's when we implement on the RPC up level, right? Infrastructure. It's very convolute to read the error message, in that case, right? So that's help to the porting. So another thing I want to mention here is like, for the C message, right? So on the send side, it add like, the data, right? So originally we are expecting it is just pass in. Now the change is just in out, right? So like receive. So I think semantic wise doesn't change much. So that's one of the argument here. So yeah.
So IO Uring also has the ability to do zero copy sends. I wonder if you've thought at all about how, like, it seems like it has a similar goal of avoiding system calls, right? And if you do a zero copy send with IO Uring, you get a completion when the send is accepted by the kernel initially, and then you get a second completion once it finishes, it's acknowledged basically, or whatever, the buffer can be reused. And there's a single system call every time you enter the IO Uring, and then that can handle the posting of completions and stuff. So it seems like that sort of is targeting a similar use case. Have you benchmarked with how this compares to IO Uring zero copy, or are there improvements? Do you think any of these improvements also apply to IO Uring zero copy? Yeah. So IO Uring notification is like a internal mechanism of IO Uring. So notification in IO Uring is very efficient. It does not introduce extra system calls. And for this method, it actually uses common socket calls. So I haven't done the benchmark comparison it with the IO Uring. Thanks.
Just expand a little bit on IO Uring because I believe this push has some merit for the socket API if you don't want to use IO Uring, but it's just an interesting observation that it looks like what IO Uring does indeed. Like you have a completion. Let's say you delay your completion a little bit instead of notifying your ePOL. A little bit different with IO Uring, but still, yeah, it would be nice to see how it compares back to back. Okay.
And it solves your problem because like it doesn't introduce a overhead in the hot path. Because you can opt to use IO Uring and then you do your request through IO Uring. And then if you don't use it, then you don't take it. So maybe that's something worth looking into.
Yes, that's true. Yeah.
Thanks.
I just want to add, for applications that already use things like message zero copy and SO timestamping, converting to IO Uring is not like a massive undertaking, right? So for those workloads, this is actually useful.
I mean, what about other like shared buffers? Like, I think BPF has a ring buffer sort of thing as well. That's typically the way that you can do asynchronous. So rather than reusing that struct message header, you can just create another ring buffer. It doesn't have to be IO Uring, I guess is my point. Yeah.
I just wanted a clarification. Maybe this is obvious to other people, but the send message requires an ACK for the zero copy completion, among other things, right? Which happens asynchronously. So is this changing the semantics of send message so that it blocks until it gets the ACK, or is it just returning completions from previous send message?
Just returning from previous send message.
Oh, so it's just so you don't have to do another sys call to get the. I see. Okay.
Yeah.
one alternative approach, I think, if you want to avoid introducing, if you want to get rid of that small cost you've added in the common path, instead of trying to use the existing mechanism, why don't you just pass in the message the address in user space of where you should store the completion? And then, those systems that need it will use that address and write back to user space, and you wouldn't add any cost at all into the common path.
That's actually my previous implementation of this method, but it has some the community had some question about the API of the message control because it somehow compromises the semantics of message control.
Yeah, I'm totally to blame for this. I thought that was not an OS abstraction to just pass a user address and say copy in here. Disagree. That's definitely V1. Yes.
I think another point I want to add is currently on the send path we do have some need, right? So to on the send back C message, we can get back some useful information in that path. So that's its add-on, right? So the one of these patch is add common mechanism to enable that. And the cost is add is 1 bit flag. So it normally people don't use that C message, right? C message will not see that cost, right? It just check that bit. That's all, right? So it doesn't affect much, but the benefit is it add the mechanism to get back, pick back the information, whatever needed. So to avoid the convolute, to extra system call, right? Because the along the RPC side, infrastructure side, with that actually it's not that convenient. That's why it's zero copy, right? Not so popular in this case. So regarding the IOU lane, so also same thing, right? So a lot of API changes. So for existing code, if they don't want to move to that direction, then this is very easy change, right? Just one flag, that's all. You get 8%, and also most application actually don't do the batch. So it don't do, okay, I wait 32, catch, then to read once. That's extra also, logic you need to put on the RPC side, right? So that's the game. Yeah.
Any other questions or comments? All right, thank you.